Hello, and welcome to this webinar sponsored by Intek, Condenser Retrofits, Upgrading Condensers Without Adding Tubes or Changing Tube Material, with Dr. Timothy Harpster, Director of Engineering at Intek. My name is Andrea Hauser, and I'm the Managing Editor of Energy Tech Magazine. I'll be your moderator today. Options for upgrading condenser performance have historically been limited to rebundling the whole condenser or changing the tube material. But recently, a lower-cost alternative has been demonstrated that should be considered by any plant wanting to increase condenser duty, prevent station power reductions, or increase heat input limited power generation. During today's presentation, Tim Harpster will discuss the process and its typical benefits. He also will discuss the performance of condensers before and after the upgrades. Dr. Harpster has led Intek's engineering team for the past 7 years, where he guides the execution of condenser studies aimed at determining the root causes of poor performance and directs the development of retrofit solutions to deliver improved performance for client condensers. Dr. Joseph Harpster, President and CEO of Intek, also will be joining us for the Q&A session. He has more than 60 years of experience in the design, analysis, and operation of instrumentation and mechanical systems. He holds several methods patents on condenser performance and air in leakage monitoring, as well as being a consultant and principal investigator to EPRI in the area of condenser performance, steam, non-condensable dynamics, and chemistry issues associated with air in leakage. The presentation will last approximately 45 minutes and will be followed by a Q&A session. Tim, please begin.
Thank you, Andrea. There are many different types of condensers. The analysis and condenser retrofit program that I'll be presenting today has been applied to main turbine and auxiliary turbine exhaust tube and shell condensers that are used in power generation. So if you're looking to upgrade the condenser, there are 3 options available, shown here. The first is a modular condenser replacement. That's a process where the existing condenser tubes, support plates, and tube sheets are removed, leaving an empty condenser shell. A self-supported tube bundle module, shown here, that is fabricated in a manufacturer's shop, is shipped on site and is maneuvered into the empty shell. The module could have a new tube arrangement, more tubes, different tube OD, different tube wall thickness, and perhaps a different tube material. And depending on the design choices, you can expect a performance upgrade. The better performance could result from cooling water flow increase due to lower hydraulic pressure drop across the new module, or more condenser surface area, or better heat transfer material. As you might expect, a modular replacement can be a very costly project in terms of labor, logistics of moving large components. And in fact, a modular replacement may not even be an option because you can't maneuver a module into the building. So another way to upgrade the condenser is a condenser retube. This is when the old tubes are removed, a new, better heat transfer tube can be selected and installed, and a very small % heat transfer increase can be expected with this option. A condenser retrofit, and the topic of this presentation, is a process whereby the current design is improved. The mechanism for improvement is the reduction of chronically air-bound regions in the original design. Chronic air binding is a widely known phenomenon. It's published about in ASME performance test codes, EPRI condenser technical reports, and was even the topic of significant research in the 1980s because the problem was so pervasive in the industry. Over on the right, I have an image of the performance profile of a Westinghouse condenser bundle. Now, this image is not generated using a computer model. It's generated by monitoring the cooling water flow rate and temperature rise across the tube bundle in many different regions and plotting the performance as a % of the achievable performance. So in this image, blue represents about 20% performance, red represents 100%, and you can see large portions of this bundle is underperforming because of air storage. And it's always this way even at low levels of air in leakage. Now I'll talk more about air storage and the 2 different types of air storage, and show more of these performance profiles towards the end of the presentation. But you can see that in this bundle there's a lot of surface area that is not performing as well as it could be. So for a condenser retrofit project, an engineering study is conducted to evaluate the existing design and various improvement options. The bundle pattern remains the same, and air binding is reduced by installing plates, baffles, pipes, to vent regions of air storage and better manage the flow of steam and condensate to maintain high heat transfer for all the tubes in the condenser. So with this process, the blue regions in the image on the right, they become red when air storage is eliminated and steam flow paths are improved. The construction can be performed with or without a retube. It's completed in a short outage length and very little risk to the plant in terms of impacting the outage schedule. The process for a condenser retrofit typically starts with a two-step engineering study. So I want to talk about the condenser retrofit process, which starts with understanding condenser performance. I was at an EPRI heat rate conference in 2009, and during the open panel session, a young engineer asked the panel, they asked, I want to make an impact on heat rate. What advice can you give me? And Joe Milton was on the panel. He's a past committee chairman of the SME Performance Monitoring Committee. And he said 3 words, but he said the same word. He said, condenser, condenser, condenser. And this table indicates to us why he gave that advice. This table is from the EPRI Heat Rate Improvement Manual. It lists the parameters most often monitored by utilities with controllable loss programs and their typical deviation. And you can see right away what tops the list is condenser back pressure. And not only does it top the list, but the typical deviation from the expected value is nearly twice that, the next highest item on the list. So the condenser is often a worthwhile component to study and improve, and improving it can significantly reduce heat rate or increase generation. So in order to find out how much of an impact can be made, an analysis of the condenser performance is the first step of the process. Well, so with instruments that are commonly found on condensers such as bulk inlet temperature, bulk outlet temperature, a measure of the condenser pressure, and some way to either measure or calculate the cooling water flow rate or turbine exhaust duty, you can calculate the total performance degradation. So you might complete a table similar to what's shown on this slide. So for example, at 10% of rated load, you might use those parameters, calculate a condenser design pressure of 2.0 inches, but the pressure gauge reads 2.6, so your excess is 0.6 inches. If you are doing the study at 100% load, you might get a condenser design pressure of 4.0 inches. The measurement might be 5.2, and so the excess is 1.2 inches. So all of this is available to you using commonly found measurements around the condenser, and it's quantifiable using average value parameter analysis. You can even use HEI methods to calculate a cleanliness factor, but that's all you can do. These parameters indicate how badly the condenser is performing, but it doesn't tell you what's causing degraded performance. And even the term cleanliness is a misnomer because there are a lot of things that can cause indicated low cleanliness factor. We classify performance degradation into these 6 categories. Fouling, everybody should be familiar with, and how dirty or obstructed tubes can increase condenser pressure. Also, if there's low flow through the condenser, then lower flow than what's being used for the calculation, then you can have an indicated low cleanliness factor. But then there's a whole other class of degradation mechanisms called air storage. Air storage is pockets of high partial pressure of air that greatly reduce heat transfer around tubes that are airbound. Everybody's familiar with problems of high air in leakage and how it can cause high condenser pressure. But similarly, low venting equipment capacity can also cause air storage. Examples of this are if the venting equipment is, say, liquid ring vacuum pumps, then a damaged impeller or high seal water temperatures will decrease the venting flow rate and result in air storage. If the venting equipment is steam jets, then low motive steam pressure or high intercondenser pressures are causes for low venting capacity. Even the vacuum equipment layout can cause air storage. For example, if you're venting 2 separate shells and the design shows that 50% of the capacity should be on each shell, well, if one shell has 80%, the other shell has 20% venting capacity, then that can cause air storage. So all of those mechanisms are wrapped in the ineffective venting column, and they can cause air storage and high condenser pressure. The last category is air binding, and whole condensers have had modular replacements because of this issue. These are bundles and air removal sections that were poorly designed to begin with and allow pockets of air to exist at all operating conditions. It doesn't matter how high the vacuum equipment capacity is or how low the air in leakage is, these pockets persist and cause excess condenser pressure for all operating conditions. So the recommended approach for the second step, the step 2 of the engineering study, is to perform a more detailed condenser test to quantify the magnitude of performance loss from each of these 6 mechanisms. And instrumentation is needed to perform this advanced evaluation. This slide shows instruments used for the advanced evaluations. ASME PTC 12.2 is used as a guideline for selecting instruments. So in addition to test grade steam pressure, cooling water inlet and outlet temperature measurements, cooling water flow is also needed. So a velocity traverse, dye dilution, and ultrasonic flows are recommended in the test codes. Differential pressure meters can also be used across differential producers to quantify flow rate after they have been calibrated. Air offtake monitors are used to measure air in leakage and vacuum equipment capacity. And finally, temperature and flow instruments are installed on the outlet tube sheets to monitor outlet tube temperature and flow rate. And with all this instrumentation in place, the 6 different components of excess back pressure that I showed you on the previous slide can be calculated. So an array of tube sheet temperatures and flow sensors in the air offtake flow measurements are essential tools for assessing air storage in condensers. Here's a picture of these tube sheet sensors installed in a condenser water box. You can see this epoxy coating that extends down into the ligament spacings between tubes. Under that epoxy are cables and temperature sensors that are scattered throughout the tube bundle. You can also see the tube flow and fouling meter that inserts into the expanded end of rolled tubes. These flow meters have a completely unobstructed flow path, so if you have ball cleaning systems, the ball cleaning systems have the balls that go right through the tubes and these meters. Over on the right, you can see a side view of the instruments installed in another condenser and the flow and fouling meter. So the data from these instruments are used to create those performance profiles that I showed on the second slide and I'll show later on. But before I show some performance profiles of different condensers, it's important to understand how air affects condenser performance. The title of this slide is Condenser Air in Leakage is Not a Problem. And I'll say that again just to let it sink in. Condenser air in leakage is not a problem. That title is meant to be provocative and challenge all of your thoughts on how air in leakage affects condensers. The reason I say that condenser air in leakage is not a problem is that if the air can enter and exist in the condenser bundle without causing pockets of significant air partial pressures, then the condenser performance is not going to be affected. So the true root cause for all of the problems that people typically associate with air in leakage is really air storage. And that air storage can occur in 2 different ways. The first way is a stagnant zone. This is where that pocket of air collects and forms at the air removal section or the air cooling zone tube section. And it's caused by air in leakage exceeding the vacuum equipment capacity. And you can see that in the image on the lower right. The second way air is stored is in air-bound zones. And these are configuration caused. And what I mean by that is that the tube bundle arrangement, the baffles inside the tube bundle, and the air removal section configuration is of a poor design and allows these pockets to persist and collect in areas away from the air removal section. And so the only way to vent them is for these air-bound zones to grow to a size such that the air that's feeding them can be exhausted from a corner of the air removal section. Now, in both types of air storage, if the tube is located in an air storage zone, then the cooling water enters the tube in the inlet water box, travels through the tube, condenses very little to no steam, and exits the tube well below the expected value. And so those array of temperature and flow sensors that I showed on the previous slide, those are installed on the outlet tube sheet and provide measurement of these airbound zones. In the next few slides, I'll show measurements from operating condensers that clearly show these airbound zones. So the first case study that I have for you is air storage as a result of high air in leakage. This is a Foster-Wheeler condenser. I believe it's a 360 megawatt condenser, single shell. The cooling water enters the bottom half of these bundles, goes into a return water box where it travels upward, re-enters the upper half of the tube bundle, and flows back through the condenser. This is the performance profile of this condenser with 5 SCFM of air and leakage. And you can see the color scale at the bottom to let you know what % of the normalized heat transfer coefficient each region is. So what I want to show you is how this condenser performs, what the performance profile looks like when air and leakage is increased. So this unit had a ruptured turbine exhaust, a boiler feed pump turbine exhaust flange rupture, and air and leakage entered through the boiler feed pump turbine exhaust port, which is located on the Bravo side of the shell, roughly where the arrow is shown. And so the air and leakage increased from 5 all the way up to about 80 SCFM. And this is the performance profile, the measured performance profile of this condenser with that higher air and leakage. You can see 2 very large stagnant zones, a larger stagnant zone in the B shell because it's closer to the source of the air and leakage, and most of it is going to that bundle. And you can see a large stagnant zone in the A shell as well. And so as I mentioned before, the way to recover this performance is to reduce the air and leakage or increase the vacuum equipment capacity to return it to the original condition. The next case study that I have is air storage as a result of ineffective venting. So again, this is when air and leakage stays the same, but the vacuum equipment capacity decreases for one reason or another. This is an Ingersoll Rand bundle. Again, this is a 320 megawatt unit showing 1 of 4 bundles. And those 4 bundles are split into 2 different shells. Here's the performance profile. You can see the air cooler zone over on the left there. That's where the air offtakes are connected to the left-hand side there. You can actually see an air-bound zone that has already formed. Notice it is far removed from the air cooler zone. And what happens in this condenser is that the venting arrangement is such that in this condition, the vacuum pump capacity is split pretty much evenly between the 2 shells. So 50% coming out of one shell, 50% coming out of the other shell. But a condition arises where one shell will receive, say, 80% of the vacuum equipment capacity, and the bundle in front of you, its capacity, venting capacity decreases to about 20%. And so what I'm going to do is animate this bundle as that venting capacity is decreased, and you'll be able to see how the performance profile changes and air storage gets worse in this bundle. So you should start to see the animation creeping along. The tube temperatures, outlet tube temperatures are providing us these profiles. You can see now that the central section is now bluer. That small circle of air binding before is now much larger. The stagnant zone has extended into the condenser, joined with that air-bound zone, and the performance profile in front of you now has the heat transfer decreased by about 40% from the original condition. So the way to recover this performance, again, is to decrease the air and leakage or increase the venting capacity. The last example of air storage, I have 2 case studies here that show air binding. And in these 2 case studies, I'll show results of a retrofit where we eliminated the air binding and recovered significant performance improvements. So this is a Westinghouse, these are Westinghouse condenser bundles. These are the performance profiles with no retrofit in place. These condensers are known to be poor performing condenser designs. You can see with very low air and leakage into these bundles, you can see it up there in the legend, the air and leakage to this shell where there's 4 of these bundles is only 23 SCFM. And you can see that the performance profile shows that about half the tubes are affected with air binding. There's a white paper available that discusses this retrofit on our website. I encourage you to go take a look at that white paper. But I'd like to show some of the results from a Westinghouse condenser that was retrofitted using this process. This is the condenser that was retrofitted. It's a single shell condenser. There are 4 of the Westinghouse starburst tube bundle patterns. Cooling water enters one side of the condenser, flows through the bundles, and exits out the other side. This is a 500 to 550 megawatt unit. And this is the data before and after the retrofit. This plot shows the condenser pressure over on the y-axis, the cooling water inlet temperature on the x-axis. The red data is the data from before the retrofit. Prior to the retrofit, the condenser had Admiralty tubes. In an effort to reduce the copper content in their effluent, they wanted to retube the condenser with stainless steel tubes. Now, just moving from Admiralty tubes to stainless steel tubes should have reduced the performance or increased the condenser pressure because stainless steel tubes have a lower heat transfer coefficient than the Admiralty tubes. So one of the motivations for pursuing this condenser retrofit project was to offset that performance loss by going to a lower heat transfer material. So again, the pre-retrofit data is shown in red for the clean condenser prior to the retrofit. And then the retrofit was installed, and there's 2 years of data after the retrofit shown in blue and teal. You can see a 1-inch pressure decrease from the pre-retrofit condition. And one thing to note is that in the pre-retrofit condition, all of that data is with the condenser operating with 20 SCFM of air in leakage. Any increase to that air in leakage, say going from 20 up to 25, increases the back pressure in the condenser immediately. But after the retrofit is installed, after we get rid of those blue regions in the bundle, we concentrate the air to the new air removal sections that are installed via the retrofit. That condenser is able to handle much more air in leakage with no back pressure penalty. And so all of that teal data shown on the plot is data obtained when the unit is operating with 80 to 100 SCFM of air in leakage. Now, there are other benefits that resulted from this project. Better condensate chemistry. I encourage you to go to the website and check out the paper. But I'd like to move on from here to another retrofit. This is an Ingersoll Rand unit. This is a 700 megawatt unit. Over on the left-hand side is the performance profile before the retrofit. On the right-hand side is the performance profile after the retrofit. So you can see side by side the impact that we have made on the air binding by installing a condenser retrofit. You can see the deep blue regions where there's essentially no heat transfer occurring in the bundle, and on the pre-retrofit side, the left side, and then after the retrofit in the same bundle, you can see those blue regions are completely eliminated. And so I have an animation prepared for you on these bundles as well. The left side, we're going to animate this bundle from 18 SCFM up to 155 SCFM. On the right side, we'll show you the after retrofit performance when the air in leakage is increased from 27 to 100 SCFM. So you should see the animation progressing, and you can see the pre-retrofit performance is the air binding has now extended all the way to the periphery of the tube bundle. The air is enveloping more tubes, causing back pressure to rise. But the post-retrofit profile, all those blue regions are gone, and the air is being concentrated to the new air removal sections. So essentially, this condenser is now more immune to air in leakage, and I'd like to show some test data in the tables below these plots to illustrate that point. Pre-retrofit, over on the left-hand side, you can see in the blue box below that a test conducted where we increased the air in leakage from 15 to 65 SCFM resulted in a condenser pressure increase of 0.8 inches. Not only that, but the condensate chemistry measurements on the condensate pump discharge showed a 12 ppb increase in dissolved oxygen. So all of the condensate falling through this bundle, going through those airbound regions, is picking up those the gases, the air gases the oxygen is dissolving into the condensate and it shows up in their condensate chemistry measurements. However, with the retrofit installed on the right-hand side, if you take a look at the blue box at the bottom, in that bundle, the air and leakage was increased from 38 to 100 SCFM. The back pressure only increased 0.2. And the condensate pump discharge measure of dissolved oxygen only increased 2 parts per billion. So not only does this bundle, is it more immune in terms of being resistant to condenser pressure rise, but it's also more immune to air and leakage because of less condensate dissolved gases. Again, there's a white paper on this retrofit at the same location on our website. This is that condenser, a top view of that condenser. It's a two-shell condenser. The cooling water enters the first stage up at the top, flows through the first stage, picking up heat, condensing steam, enters the second stage and goes to the second stage. Both shells are isolated, so the second stage operates at a higher pressure than the first stage. Both of these condensers are attached to LP turbines. And so I want to show some data from this condenser retrofit. The retrofit occurred in 2010. I'm going to show you data dating all the way back to 2006. So again, this is a similar plot to the one I showed you before, but with much more data. There's condenser pressure over on the y-axis, cooling water temperature on the x-axis. The red data is an entire year of data filtered for full load for the second stage condenser shell. The blue data is all of the data for the entire year of 2006 for the first stage condenser shell. Here's data for 2007. I faded the data from 2006 into the background. This is the entire year of 2007. This is the year 2008. This is the data from year 2009, and you can see some of the first stage pressure up at the second stage pressure. This is because they had an isolation failure between the two shells that caused the first stage shell to operate at the second stage pressure. But that problem was fixed at the end of 2009, and all of 2010 it remained in good working order. So this is how the condenser, this is the last time the condenser operated in the pre-retrofit condition. The retrofit was installed at the end of 2010, and this is the 2011 data. This is after the retrofit was installed. You can see a 1-inch pressure decrease in the second stage pressure, a 6/10 decrease in the first stage pressure, and that resulted in an 80 BTU per kilowatt hour heat rate reduction. And in the summer months, when they operated in the heat input limited mode, was an additional 6 megawatts of generation. When taking a look at any upgrade, condenser upgrade project, there are some special considerations for pursuing one of these projects. That provide additional economic incentive. If the condenser or if the unit is going through an upgrade where more steam is being put into the condenser than it was originally designed for, then a condenser retrofit or upgrade process might be able to offset that pressure increase. The second special consideration is if the unit ever operates with seasonal or permanent heat input limited conditions. So anytime you reduce the condenser pressure through an upgrade process, you're actually able to generate more megawatts. And so anytime you're able to generate more megawatts, the payback period drops from something like 2 to 3 years to under a year. If the unit has variable frequency drive cooling water pumps, then you can save station power by throttling back on your cooling water pump power and deliver more to the grid. And by reducing the condenser pressure, it gives you that flexibility to throttle back on your cooling water usage. If you have cooling tower units that result in high inlet temperatures, then any percent increase in heat transfer has a greater impact on the condenser pressure. So if the unit operates with high inlet temperatures, then there's additional economic incentive there. If the unit has a scheduled retubing and the unit is known to be a poor performing condenser, then when the unit is being retubed, that is the optimal time for implementing a condenser retrofit, because all of the tubes are out. You have more flexibility to alter the interiors of the condenser, you also have a crew already on site that's doing the retubing. They have the skills necessary to install a condenser retrofit, and so there's labor savings there. Also, if it's a retrofit that's of similar design to one we've done before, then there may be some engineering evaluation reduction there. So step 4, what occurs during a retrofit? Obviously, the retrofit is designed, parts are designed, sub-assemblies are designed, and the assembly process is put together. Parts are provided and any job-specific tools. Really, any general contractor with experience can install the retrofit. There's no special materials, no special tooling or special chemicals involved in the condenser retrofit, so it's pretty straightforward work. We would support the contractor on-site with on-site supervision to ensure that the retrofit is installed as it is designed. And then, of course, there's a post-retrofit performance assessment where the performance improvement is quantified. To give you an idea of the types of materials that are used in a retrofit, I've shown a few pictures here of materials that are staged for the 600 megawatt condenser retrofit. You can see over there on the image on the left, it's mostly carbon steel or stainless steel parts. There's some smaller parts in the small parts bin up here. And of course, the condenser may need to be scaffolded so that crews can get into areas and install these parts, weld them in place. So here are some conclusions. Poor condenser performance is often blamed solely on cleanliness, but it is more often a result of many different factors other than dirty tubes. Putting a microscope on your condenser quantifies the impact of individual performance degradation mechanisms, and with that data, you can make informed decisions and correct only those mechanisms that are economically justifiable. Many condenser designs remove air poorly and operate at much less than their potential, and these designs can be fixed by a retrofit with great improvement in condenser performance.